Welcome, this is Coach Dorf. We're going to continue our discussion about calculus and talking about optimization problems. Here we're going to do an example of a problem that's similar to the homework. So in this problem, we're given that we have 1,200 square centimeters of material that's available to make a box with a square base and an open top. And we're supposed to find the largest volume. All right, so here's going to draw a picture of my box. It looks something like this. And because it's a square base, I'm going to call X the length of each side of the base. So X equals the length of each side of the base. Now the height is not related necessarily to the base, so I'm going to have to give a different variable for that, and I'm going to call that y. All right, and this is doing what I would call step one. I'm going to find my variables, and then I'm going to find an equation that relates x and y. Well, what is the equation I'm going to use? It says that I have 1,200 square centimeters of material to make the box. So that's going to include then the area, the surface area of the base plus the four sides. This box doesn't have a top, so I don't have to worry about the top. So let's look at these. So if this is my base, I have the lengths of x and x, and so the area of the base is going to be x squared. If I have a side, it's going to look like this, where one length is going to be x and one's going to be y. So the area of each side is going to equal x times y. But I have four sides, so four sides have area equal to 4x. And there's no top. So in that case, the area is 0 for the top. So the total area, total surface area of the box is going to be the base plus the sides. And again, we're going to use the 4xy and the x squared. And we could add the 0 in there, but that doesn't really affect it because it's 0. And so this is all supposed to equal 1,200. So that's my equation, then connecting the x's and the y's. The second thing I do now is, what do I want to minimize or maximize? Well, I want to find the largest volume. So we want to maximize volume. So what is the volume? Well, the volume is going to be the area of the base times the height. So x squared plus y. Now, that's a variable, that's a function with two variables, x and y. We want to get it so that we have a function with just one variable, because that will make taking the derivative and finding the critical numbers easier if we do that, and that will make it easier to find the max and minimum values. All right, so how can we do that? Well, we're given that the volume is x squared y, and we also know that x squared plus 4xy equals 1,200. So we're going to take the second equation and we're going to solve for y. And we're going to solve for y because it's just easier to solve for y on this one than it is for x. So to do that, I'm going to bring the x squared to the right side by subtracting it. And then I'm going to divide by 4x. So I get 1,200 minus x squared over 4x. And that's going to be my y. And now I'm going to take that here and I'm going to substitute it in for y here. When I do that, then I get volume is x squared times y, which now if I substitute it in, I get 1,200 minus x squared all over 4x. And when I want to simplify this, so I notice I've got an x in the denominator and I have an x squared in the numerator, so I can cancel those out, but that leaves me another x in the top because it's an x squared. So when I multiply those together, then I've got 1,200x minus x cubed over 4. And so then I can write that as v of x is 1,200 over 4x minus 1/4 x cubed, which I can do one more step and I'll write that as 300x minus 1/4 x cubed. All right, this is then the function that we want to maximize. We want to find the largest volume there. So now we do in step 4, we're going to use the second derivative test on this one to find the critical numbers and then find out which critical numbers gives us a maximum. So I've got my function v of x equal to 300x minus 1/4 x cubed. So I take the derivative there and I get 300 minus 3/4 x squared, and I set it equal to 0 because I'm finding the critical numbers. All right, that gives me then that 300 equals 3/4 x squared, and I want to solve for x. So I'm going to multiply both sides by 4/3. I could divide both sides. I could divide both sides by 3/4, but I think it's easier to multiply by the reciprocal, which is reciprocal of 3/4, which is 4/3. Because when I do that, then on the right side, the 3's cancel out, the 4's cancel out, and I'm just left with x squared on the right side. And on the left side, the 3 from the 100 and the 3 that's in the denominator under 4 cancel out. And so I'm going to have 100 there. So I'm going to get 400 equals x squared. And when I take the square root of that, I'm going to get 20 or negative 20 equals x. But we don't want any negative distances, so we'll cancel out the possibility of negative 20 being a critical number for this particular problem because we're dealing with distances. So x is going to equal 20. So that's my critical number for the problem I'm working on. And now I need to figure out whether that's a max or min. So I take the second derivative. In doing that, we go back to the first derivative. Here was the first derivative. So I'm going to take the derivative of that to get the second derivative. So derivative of 300 would be 0. Then I've got minus 3/4 times 2x to the first. So that's going to equal minus 3/2 x. All right, and so when I look at the second derivative at the critical number, I'm going to put 20 in there, so minus 3/2 times 20, all right, which is then going to give me negative 30, which is less than 0. So when I have a second derivative less than 0, that means I've got a minuses, a second derivative, so I put 2 there, and I get a frowny face. And at the top of the frowny face is where my critical value is. And because it's the top of a concave down thing, this will give me a maximum at that critical number. So we're saying then at x equals 20, we get the maximum volume. Now I need to go back and the last step is to figure out what my answering the final question. And the question again was to find the largest volume of the box. So we're supposed to find the volume, find the largest volume. So to do that, I will go back and remember that my volume we wrote as 300x minus 1/4 x cubed. So volume equaled 300x minus 1/4 x cubed. So now I'm going to plug in 20 there for x, and I'm going to get 300 times 20 minus 1/4 times 20 cubed. And if I pull out a calculator and simplify that, I'm going to get 4,000, and that's going to be cubic centimeters because I'm dealing with volumes, and that's my final answer. And it's okay that I didn't solve for y here because I'm answering the question, find the largest volume, which I got there, which was 4,000 cubic centimeters. All right, hope that helps.